Hey everybody, welcome to Fabulously Fun Physics with Miss Segovia and
Mr. Flint.
woohoo! Alright, let's go over the responses and the explanations for this fantastically fun worksheet. So the first question you had, the graph above represents the motion of a cyclist. The graph shows that between t equals 0 seconds and t equals 2 seconds, the cyclist is... What do you think? It should be increasing in speed. Because if we look right here, we're seeing the velocity, and over time the velocity is indeed increasing. Next question. A ball is released from rest at the top of a ramp at t equals 0. What is the speed of the ball at t equals 4? So if we want to use our guess method, we can give our variables, our givens. So we've got initial time equals 0. Our final time equals 4. And then what else do they give us? If we look at our graph, we have the acceleration. And acceleration here is constant at 2.5 meters per second squared. And that should be seconds and seconds. So what formula could we use that'll help us solve our unknown, which in this case is speed, or we could also say velocity? Well, that's right. You could use acceleration equals velocity over time. And so if we sub in our numbers there, we've got our acceleration is 2.5 meters per second squared. We've got our unknown velocity, and our change in time would be 4 minus 0, so we can just shorten that to 4 seconds. And when you solve that for v, you should come up with 10 meters per second. So the correct answer is H. In the graph of Marty riding his new moped, what is the position, speed, and acceleration during the first 3 seconds? Well, after walking all those graphs, you guys should know that from here to here, he is standing at the 100 meter mark, but he is not moving and therefore not accelerating. Love that one. What is Marty's speed at position 60 meters and the time of 7 seconds? So if we look at that one, we're looking at this point right here. And Mr. Flint, how can we figure out that one?
Well, you need to find the slope of the line. So we can start at 3 seconds and go all the way down to 10 seconds. And basically that's a change in 7 seconds of time, and then we would need to figure out the change in position. So at 3 seconds it starts at 100 meters, and at 10 seconds it's down to 30 meters, so that's a change in 70 meters. So we're looking at a change in 70 meters of displacement, and then we are looking at a change in 7 seconds of time. So we can just divide the displacement of 70 meters by a time of 7 seconds, and that will give us 10 meters per second.
10 meters per second. Sorry, I wrote that funny. 10 meters per second. You know what it should be. All right, what's the velocity and what direction and time at 15 seconds? So right here. And we can do that one pretty similar to the way we did the last one by just taking our average velocity right here. So our average velocity, our distance over our time. So on that one, we've got our distance is going from 30 to 90, and our time going from 13 to 17, so that's 4 seconds. And so once we figure that one out, we should end up with our velocity being 30 meters per second, and oh wait, I'm looking at the wrong one. So 30 over 90 is 60 over 4, so that is 15 meters per second, and our direction is positive. Flint, you want to take number 11?
If we're looking at number 11, that's where Marty had mechanical difficulty and stopped during the trip. The only place where he stopped once he started was in the middle, between 10 seconds and 13 seconds, and you know that because the slope of that line is 0, and the slope of the line on a position time graph represents velocity. So if the slope is 0, the velocity has to be 0. Therefore, Marty is not moving at that point, so he must have had mechanical difficulty at that point.
And at that point, he was at 30 meters, and he stopped for 3 seconds.
Yep.
All right, so now we're off to the races, and we've got two A and B moving at different times. And so this one, we can just look at the graph. No math involved. Awesome. So who has the lead at t equals 0? Well, that's right at this point. Line B or line A, and that would have to be B. Who's moving faster? Well, take a look. Who's going to end up winning that race? That's A. And why do we know he's going faster? He has a steeper slope. So A again.
So you can see it visually, but you also know that that person is moving faster because it covers more distance. Line A covers more distance in the same amount of time that B does. B covers less distance. Line A covers more distance, line B covers less distance, both the same amount of time. Therefore, line A is moving faster, line B is moving slower.
Yep. And at the end of 2 seconds, who is ahead? Very simple, line B. B. All right, and which of the displacement graphs above roughly correspond to the velocity graph shown in the graph below? After playing with your carts and ramps and walking back and forth lots and lots of times, hopefully you chose letter C. And why would it be letter C? Well, right here we're at a positive velocity, but we're slowing down and approaching 0. And so when we look at this graph, we start with a positive velocity, and then we eventually approach 0. Same thing.
So if you draw tangent lines, at the very end, a tangent line would be 0 slope. It would just be a flat line. So that means that the velocity there is 0, that the person is staying about, it looks like 6 meters away from the starting point and just staying there, not moving anymore. So it would have to be approaching 0 velocity. At the beginning of that line, you can see that it's pretty steep, so the velocity is going to have to be fairly large. So you can see that steep, large velocity, so we'd have a large number at the beginning.
And a related question, which of the 4 graphs A, B, C, or D used in the previous question would resemble a graph produced by a picket fence being dropped through a photo gate to measure the acceleration of gravity?
Anytime you drop something, it's going to have to start at 0 velocity. And on a distance time graph or a displacement time graph, that means the slope of the line is 0. So if you look at D, that's one of the only ones where it starts with a 0 slope. So if you drew a tangent line there, notice that it's a flat line at the very beginning, meaning that it is standing still. No velocity. If we look at B, B also has the same thing, but as time progresses, it goes back to 0. Well, if you drop an object, its velocity is not going to suddenly go to 0. Well, that is unless it hits the floor. As soon as it hits the floor, it'll drop. But we're assuming that thing has not hit the floor. So that slope is going to be continually increasing. So coming back to D, you can see if we drew tangent lines along the way along D, it's going to have an increasingly the slope is going to be continually increasing. So therefore we know the velocity is going to be continually increasing with D.
And our last ones for today. The graph above represents a car driving down a straight highway. Which of the following is the acceleration of the car at t equals 4 seconds? Right there.
All right, so we're looking at this one here. So the graph above represents the car. Which of the following is the acceleration of the car at t equals 4 seconds? Oh, well, if you look at the slope of this line, the slope of this line is constant, so it'd have to have constant velocity. So constant slope, constant velocity. if it has constant velocity, then it can't be accelerating. Think about, when does your car have constant velocity? Well, when you put it on cruise control. And when you put it on cruise control, you're not accelerating. And you're not speeding up, you're not slowing down, you're staying at one speed. So this object would not be accelerating.
So our answer, awesomely, is 0 meters per second. And so the graph squared, sorry, my bad. The graph above represents the motion of a car. Based on the graph, the car is most likely, you should know from that last test, it is not driving up a steep hill. Since we're not curving, there's not a parabola, we are not speeding up, and as Mr. Flint just explained, it is driving at a constant speed. We also know it's not decelerating because we would see a negative slope on our line. So we could eliminate that one as well. So I know you're sadly disappointed, but that takes us to the end of the packet. We hope that helped. If it didn't, please come see us. Ask for help. We're here for tutoring almost all the time. Thanks.
Bye.
Bye.